Here we are again. This time we will talk about anhydrides. All right, so an anhydride molecule, um, as I mentioned in the previous videos, is to be thought of two carboxylic acids that have been fused together, condensed together, and in the process, you have lost a water equivalent, right? Hence the name anhydride. All right, so as far as how you name these things, you name them as you would normally name a carboxylic acid. And once you do that, the only extra requirement is that you add the suffix anhydride at the end of the name. So, generally speaking, it's not too difficult to name these things. Now, there's a possibility, however, that one side of the anhydride will be different from the other side. So if that's the case, then you first got to name the two carboxylic acids alphabetically in respect to each other, right? So for instance, if you have butanoic acid and you have ethanoic acid, then butanoic acid goes first, then ethanoic acid goes second, and then you end up with the suffix anhydride. All right, so let's start with some examples though. All right, so if this is fully symmetrical, right, we have two carbons on the left side, two carbons on the right side. From the point of view of the middle oxygen, then this is simply a derivative of acetic acid, right? So we just call this acetic anhydride. Now you could also call this ethanoic anhydride or ethanoic anhydride for an alternative name. That's the IUPAC name altogether, but one or the other is fine with me. Although acetic anhydride is the more commonly used name. All right, now here on the other hand, we have two different carboxylic acids, right? Almost the same in structure, except that the substituent pointing down on the left side happens to be a hydroxy, whereas the substituent on the right side happens to be a methyl. So what you should realize is that the carboxylic acid on the left side of the molecule is lactic acid, right? Whereas the substituent on the right side is simply propanoic acid with a methyl substituent at position 2. So you have lactic acid versus propanoic acid, right? So lactic acid will be the first one to be listed because of alphabetical priority. So lactic, then we have the 2-methyl propanoic, right? So lactic, 2-methyl propanoic, and then you end up with the word anhydride. So they're not too bad generally speaking, but you just gotta keep that alphabetical order in mind. All right, so here's another one, right? If we look at this one, you should realize that the left side is technically benzoic acid, right, or derived from benzoic acid. And then the right side is just a regular cyclohexane ring that happens to have a carboxylic acid moiety attached to it. So that one is just cyclohexane carboxylic acid, right? So as far as naming it, you would just say um, benzoic, right, because of alphabetical priority. And then you have cyclohexane carboxylic. So you say benzoic cyclohexane carboxylic anhydride to complete the whole name, right? And notice that in all the names, we are dropping the word acid, um, you know, prior to adding the word anhydride. So just be careful with that. Okay. Now, as I mentioned to you, right, the dicarboxylic acids can easily form cyclic structures that can also be considered anhydrides because you're kind of fusing these two carboxylic acid together. And usually this is going to happen if you end up forming 5 or 6 member rings, generally speaking. Those are like the more stable ones because the bond angles are just right in that, sp3 hybridization, within the ring carbons. But okay, to kind of give you an idea right here, right? So if we start with phthalic acid, right, the carboxylic acid moieties are pretty much right next to each other. And, you could argue that they are pointing towards each other. So if you basically allow for a reaction to happen, and we will talk about how this happens, in a later video within this lecture, pretty much these things can come together. And if you count from the oxygen all the way around to the second carbon, or the second carbonyl carbon specifically, it takes a total of 5 second row elements to make that trip. And so when this fuses together to form the anhydride, um, you will get the following molecule, right? And then notice once again, two H's plus an oxygen are basically gone by the time we cyclize this thing entirely. That's what the formation of an anhydride is all about, removing water from the molecule. But this, which derives from phthalic acid, will have to be known as phthalic anhydride by default. Same thing goes for the other dicarboxylic acids. You can start with succinic acid, and if you count it, right, you have from the oxygen, you have 1, 2, 3, 4, 5, all the way down to the second carbonyl carbon. So this will form a 5-member ring. And the best thing is to label, like number these atoms so that you know where things are going to fall. Like what you can see right here is that, yeah, position 2 is where the carbonyl at appear. At position 5, you ought to have the other carbonyl, right? So when you draw your 5-member ring, they should be, a position, one position away from the middle oxygen, right? The thing that's kind of linking them. And then everything here kind of makes sense because if you start with oxygen as being position 1, that's position 2, then this is 3, 4, and 5. So obviously for the simple molecules without substituents, this is a bit of an overkill. But once you start having substituents, this might help you out big time to figure out where things land once you cyclize the molecule. Okay, and of course the name, right? Since it's derived from succinic acid, this is succinic anhydride. Okay, and just another example, glutaric acid, starting from the oxygen on the left side and going all the way to the second carbonyl carbon. Now we're covering a total of 6 carbons. So this will be now a 6-member ring. And yes, you will have the anhydride, moiety present in that ring. So this will be known as glutaric anhydride. Okay, and then one more to complete the series because, the OCD just kicks in. I have to make sure that this PowerPoint is as symmetrical as possible. If we have maleic acid, starting from 1 oxygen and making our way all the way to the second carbonyl carbon, here we have 1, 2, 3, 4, 5 carbons, right? So this will become a 5-member ring. And not only that, but at positions 3 and 4, you still have to have that double bond, right? If you don't do that, then you're giving me a different molecule altogether, right? If you forget about that double bond, well, this is not going to be maleic anhydride. It will be instead succinic anhydride. So you got to be careful, not to forget about those additional functional groups, additional substituents, etc., etc. Okay, so that concludes the nomenclature of anhydrides. In the next video, we will talk about how to name esters. All right, so see you then.